So it's wonderful. I've been looking forward to your talk, Anahí, about angular momentum loss in BE stars. So just a very brief little introduction about Anahí. Anahí was born in Bariloche, Argentina, and she did her undergraduate studies at La Plata University in Argentina, and then she moved on to her thesis with Lydia Seidel in the topic of IR spectroscopy of BE stars. After she finished her PhD, she moved to Geneva under George Manet's group until 2015, and she worked on the evolution of stars and the link to the BE phenomena. In 2015 and 2016, I was happy to say that we had Anahí come to Western University to work with myself and Aaron Siggett as a postdoc. And we worked on, of course, BE stars and disk models. And then she moved back to La Plata and was a postdoctoral researcher in 2017-18. But since July 2018, she has a permanent position at Connecticut first and since mid 2019 at the University of, I'll say it wrong, National University of de Rio Negro. Is that right, Anahí?
Perfect. Yes.
Okay. And she teaches math and engineering students depending on the semester. And we are very delighted to have you here to talk about your research. So anytime you're ready, you can go ahead, Anahí.
Okay, thank you very much. Before I start, I want to say that I'm very happy to be here with you today. I have not been that present in the BE community the past years. Well, things have been tough, but also very nice family things happen. So I'm trying to go back slowly. So today, as the title says, maybe it was a little bit ambitious, revisiting the angular momentum loss rates for BE stars in the single star scenario. And of course, I should have said that I will give my own vision or perhaps show what I've been working on. And before I start, as Carol said, I'm working currently in the University of Rio Negro where I teach. And it's also the institution where I live my academic life. And I'm also a researcher from CONICET who pays for most salaries for researchers in science in Argentina. And we are able to move once we belong to this institution, we can move around. So I was in La Plata working with the group where I formed. I still collaborate with them, I work with them, but I'm living here in Bariloche, as you can see in the picture. This is very close to our place. It's a nice, this is Lago Mascardi, not far from here. Very beautiful landscape. Some of you may have been here. Just in case you haven't, here you can see a map, South America on the left. And there's a zoom of our country, Argentina. And there you can see a brownish region that's Patagonic desert. And on the left, very, very close to the Chilean border with Chile, it's us in the red point. That's San Carlos de Bariloche, this town. And we are trying to start our little astronomy group here with other two astrophysicists from La Plata as well. And we're struggling, but it's nice. It's a nice experience to be back in my hometown with my family, trying to work in astronomy. So, of course, I'm still working in collaboration with researchers of different places. What I will show today is mostly work in progress, quite evolved, in collaboration with a group in Geneva, led by George Manet, and mainly the person who is mainly working with me in this is Sébastien Martinet, Sylvia Ekstrom, Cyril Georgi. Also, we are counting on the collaboration of Sayo, Hideyuki Sayo from Japan. This is most of what I will show today, and I will show a plot. Also, work in progress of Maziar Karishi. That's why I don't want to spoil what he's doing. I will show just a small plot, I will say. So, first of all, I want to put in context of what I want to show you today. In 2013, the Geneva group published different grids of rotating models between 1.7 and 15 solar masses with different rotational rates as the zero H-main sequence. Well, for 3 different metallicities, SMC, LMC, solar metallicities. And for these models, mechanical mass loss, this is extra mass loss that was computed once the star reached the critical limit, which is assumed to be 0.99% of critical because of numerical reasons. That's the moment where the star has this extra mass removed from the star. So that's what was computed in 2013, and by Georgi was the first author. And we also had a paper too, very linked to this first article, where we investigated the link between the rapidly rotating models and B stars. So at that point, we made very strong assumptions. The first one is that only stars rotating at the critical limit lose mass mechanically, and that's a very strong. And then, but this is because the star can, there's no other mechanism involved in the mass loss, which we know that may not be the case currently. Then we considered a stationary disk attached to the star, following the prescriptions given by Kritichka. I think he was around in 2011. So in this scenario, the star provides the disk angular momentum, and this sets the mass loss rate. So in that article, we published this table where you can see in blue, in a blue marked region, is the ranges of angular momentum loss rate through the disk, because we also consider the following the prescriptions. Well, we have the angular momentum loss in winds, but also in a possible disk wind if present. But we have the angular momentum lost through this disk. And as is marked here, we consider the disk is isothermal. This corresponds to this P equal to 0. And also that the alpha parameter, the alpha viscosity parameter is 1. So these are very strong assumptions. But this was our first attempt to do this. So I think it was pretty interesting, at least to see. So basically these two, and maybe there was a third one in the series where we explored populations of rotating stars, provided different parameters or quantities that could be tested with observations. And this way we could learn more about rotating stars in general and B stars in particular. Of course, at that point, we not only had angular momentum loss rates and mass loss rates to disks, we could also have surface abundances of different elements for rotating stars. And these are many of the aspects that were explored in relation to these models. Of course, there are many other papers. I really apologize for not mentioning them here, but I feel that if I mention some of them, I will not mention others, and I just don't want to do this. I wanted to focus on what I wanted to tell you today, so I apologize really for the lack of information on other people that have worked on rotating grids. There are others, of course, but I'm just telling what we did from 2013 and up to the moment. So then, following this thing that we had parameters or quantities to be tested against observations or other data derived from observations, what's the angular momentum loss rates? In the picture of the right, you can see some colored lines. This indicate the values of the angular momentum loss rate obtained by our models in 2013. And we see a hatched region occupied by the data from an article from Rimulo et al. 2018. This region or these ranges of angular momentum loss rates were obtained for 54 SMCB stars that undergo events of this formation and dissipation. They basically, of course, the paper is a very nice article, and many of you may know it well, but basically they made a grid of synthetic light curves, setting different parameters for the central star and also for the disk parameters, and then they fit the light curves and obtained, in particular, they obtained viscosity values, which was very nice. But when they compared the angular momentum loss rates to our values or our quantities of 2013, we see that there is a difference. And this was also seen in a paper by Vieira et al. 2017. If you go back to them, and maybe many other pieces of work, but we are focusing on this. So what we assume as a working hypothesis is that Rimulio et al. 2018 loss rates describe adequately what happens in B stars. We know that, of course, the values they get are model dependent as well. But if for a moment we assume that the values are reliable, is there anything that we could do from the stellar evolution code, single stellar evolution code, to help reduce the differences? Of course, modifying the physics or the prescriptions that we have in the code is not the only solution. There are other scenarios that can lead to the formation of B stars, but we are exploring this one. So and we have to do it. So it's something that we needed to do. So following what the Geneva code, as all stellar evolution codes, are dynamic, and they are constantly changing and improving. And relative to our 2013 paper, improvements have been made in the angular momentum conservation equations within the star, mainly the treatment of the envelope coupled to the interior, and how the angular momentum is conserved, and how the border conditions are set. So some improvement have been made, and we needed to see whether these have an effect on the angular momentum loss rates that we had. And basically, as I will show in a plot later, this is not the case. Luckily, the changes or the improvements in the code show that what we did before was a good approximation, or they didn't affect the results significantly. They change, but in a very slight way. The evolutionary tracks are the same, and the loss rates do not change significantly. So another thing that we could do was to make other modifications on the physics of the stellar models that could help reduce these differences. So one of the natural things to do was to modify the transport efficiency of angular momentum and chemical elements within the star. This was something done by Sébastien Martinet, and basically a free parameter was introduced in the equations of transport of angular momentum and change of abundance of chemical elements in order to diminish the transport efficiency. So this parameter was set from 1. 1 is the same efficiency that we have without making any change. And then this factor was put 1/2, 1/10, up to 1,000, well, 1/1000, to see how, what the effect was. So two things were done. Difference efficiencies were considered directly from the 0 HVN sequence. And, but these, what you can see the table on the right, the values do not change from 1 to 1/100. The effects are seen only when the transport is significantly reduced to 1,000. And this has effects on the surface abundances. While we don't see a significant change in the angular momentum content, which is on the second column, I'm sorry, angular momentum loss rate, on the right column, we see that the last value goes to 0, basically because the star doesn't reach the critical limit as defined in our work, which is reaching 99%. We also, of course, when we start with a different transport efficiency, like directly from the 0H main sequence, the evolutionary paths are very different for all of them. So it's hard to compare them. The time scales, the duration in the main sequence change. The surface or the stellar temperature and luminosity are not the same. Well, the luminosity is not that different, but the temperature is not the same for these models. So it's hard, it's tricky to compare how these mass losses are affected. So another thing that was done by Sebastian was he considered the point where the critical velocity is reached, as defined here in our work, and he set different transport efficiency there, and he computed the values. And basically, we find that modifying the transport efficiency does not contribute significantly to reduce the differences of the evolutionary values and Rimouleau et al. Values, except for the value when the efficiency is very, very low, and basically we don't have any mechanical mass loss. So that the stars never reach the critical limit. The next thing, or another thing that we could do was to change the critical rotation limit. We have assumed, as I mentioned before, that the critical limit was set to 0.99. I'm sorry, I think I put it in a slide before, but omega crit is omega over omega critical. So here is 0.99. So the rotational rate, the critical rotational rate is 0.99. So this means that the star can lose mass mechanically when it reaches this value in the code. But then what we do is, okay, let's assume that the star starts losing mass when it's rotating, for instance, at 0.7 or 0.8, 0.9, to keep rotating below that value. What do we have? Again, this is an example for setting the limit at 0.7. And as you can see, the order of magnitude is very similar to the ones that we had in previous slides. But in addition, changing this upper limit, or changing the maximum limit for the, or changing the limit for mass, mechanical mass loss, leads to similar angular momentum. But instead, as the star is rotating at this rate from the whole main sequence, and it needs to lose quite a lot of mass, the final mass lost is quite big, which I think it's not observed. It's around 2 solar, I think it was of the order of 1 solar mass for a 9 solar mass stars, which is a lot. So far, the proposed modifications do not significantly contribute to reduce the difference. So here in the plot on the right, I plotted the same figure in slides before, where we can see Rimouleau's hatched region, our colored curves that show what we had in 2013. The gray lines indicate the trends when all the new computations consider that the code is a new one, the new version of the code. So setting the 0.99 limit, which is the upper curve, which would be exactly the same as the red, well, it would be the the blue curve. It goes a little bit down, but it doesn't go that below. Then if we change the limit to 0.7, we go a little bit down, but we are still up there. And then if we change the transport efficiencies, we go to the colored regions here. We have in pink the effect of changing the efficiency when rotating at 0.99 and 0.7, and also modifying the transport efficiency. So we are a little bit, this is for a single model of 9, but the results do not in general contribute to decrease this angular momentum loss rates. And this is, at this point we said, okay, maybe there's nothing we can do. We are setting rotation as a unique process involved. That's basically what we have been doing here. The star, we allow the star to rotate as fast as it is possible, and then mass is released. Is there anything else we can do from the single stellar evolution scenario where we cannot account for other processes adequately? And then we were at this point asking ourselves whether we were making things that made sense or not. Maybe they don't, I don't know, but new ideas come, luckily, and we said, okay, maybe we can do something. Maybe we can try to mimic an unknown mechanism that eases mechanical mass loss when the critical limit is approached, but below the critical limit. Maybe air mode pulsations, as proposed by Sayo, is this mechanism. We know that B stars show variability. Different authors have different interpretations of these variabilities. Sometimes they seem, most people or everyone seem to accept that B stars pulsate. They have pulsations, but what is a mechanism capable of helping the stars put material into a disk, in particular when the star is rotating below critical? There are different pieces of observation showing that B stars, some of them rotate very fast, very close to the critical limit, in particular in the late B star domain. But in the among the early B stars, we see B stars that may not be rotating that close to critical. So we need a mechanism strong enough to put material there, and then allow viscosity to put this material into a disk and make it evolve and form the disk, the beautiful disk that we observe and many people here model and observe. So what we propose here is to mimic this unknown mechanism. And this is something that, okay, we are trying to mimic this unknown mechanism, trying to put some ingredients that can make it more realistic, or at least to try if this can be done in the future, to help understand the mechanism, the underlying mechanism by trying different laws. What we have here is okay, let's allow mass loss when the star rotates, for instance, be above, oh, here I have a W, it's omega. I'm considering omega as before. This is omega over omega crit, the angular momentum velocity over the critical point. When we assume that when it's 0.8, the star can begin losing mass, and this mass will be increased up to when critical limit is reached. What we do in the code is to modify a parameter called dm-mid. This is in a subroutine called wind, where the mass losses are treated. And once when we have time step, and in this time step, the amount of angular momentum that is put in the outer part of the star exceeds, makes the velocity exceed the critical value, or the value that we want to set as a limit. This is removed. All this matter is removed and then recomputed what the new velocity is. And this is the new velocity for the following model. So this is what needs to be kept below a limit. But if we assume that the star can lose a fraction of this matter needed to keep it below rotating, for instance, 0.8, when we allow the star to continue evolve rotating towards the critical limit while losing mass. This, if we look at the evolutionary tracks, this has a very poor effect in the evolutionary track. It doesn't affect the evolutionary track. The star evolves very similar to a star that rotates that reaches its critical limit towards the end, because the masses lost are not very big. And so in this prescription, then I will read my last sentence because I started to speak and I went. In this prescription, when the stellar evolution makes a rapidly rotating star evolve towards a critical limit, the mass and angular momentum loss rates increase significantly. So when we propose this kind of prescription, which is for the moment absolutely arbitrary, I should say, but it has some relation to what is observed, or may have some relation, we are assuming that we start losing a little mass and a little angular momentum when we start losing, and the star is not rotating that close to critical, when it increases towards when the star goes towards the critical. So what we did next here is, it is a plot showing some of the models we computed. We put this 0.1 limit when it was rotating at 0.8. If we consider a smaller, we tried different laws, linear, power law, small value of, but sometimes we get the angular momentum loss rates go really low. Some of them don't have it. If we consider it's higher, we don't have we don't have a significant effect. So we kept these values just to have something to work with. And we obtained these angular momentum loss rates. Of course, we average in the mechanical loss phase, which goes from the moment it starts losing mass towards the end of the main sequence in this case. And as we have different regimes of angular momentum loss rate, we split the mechanical loss phase into 3 regions of equal angular momentum loss, each of them during differently. I can make this clear later, but we just split it in 3 different of equal angular momentum loss rates, and they have different durations depending on the regime we are. So later I put this into the plot we had before. The blue rectangles here indicate the ranges covered by the new prescription, and the yellow circles indicate the angular momentum loss rates the star is more likely to have during the mechanical mass loss. If we go to the previous column, this, I didn't mark it, I'm sorry. The 4th column, which shows the mean angular momentum loss rate in this phase, is the one that lasts the longest, and is plotted in yellow, I'm sorry. So we start to go into the region covered by models. So this is particularly true for stars above 9 solar masses. As you see, we have these yellow points and the blue marked regions falling together with the observations, or the region, the angular momentum loss rates derived from observations by Rimula. But we don't have small mass stars below 7 solar masses. These authors covered only relatively high mass B stars, but the values we have seem to be close to the original computations, or the ones that consider rotation is close to critical. We cannot say much because we don't have many stars, but this is what I want to say in the next plot. But it's possible that late B stars are closer to the critical limit, and maybe a prescription like the one we're proposing is not necessary here, or the angular moment. Maybe if stars start having some activity or start losing mass before, maybe this is too few and it doesn't help them lose mass. I don't know. So the thing is that so far we have assumed that the data by Rimulu et al. Represent the real nature of stars, of B stars. But the thing is that of course, the way they derived angular momentum loss rates is model dependent. So we asked, okay, are we relying? The good thing of this is that even if those angular momentum loss rates obtained by them in 2018 turn not to represent that good the nature of B stars, we can also test other scenarios or prescriptions for the angular momentum loss rates and try to explore what of these prescriptions help to represent them adequately. So this prescription, this new prescription that we have seems to go well with these values they obtain. But of course, future observations may provide better constraints on this, and maybe we can have other prescriptions. So then another approach, and here in this plot is a stage where we are now. I think that it's interesting that this allowing the star to lose mass progressively before it reaches the main sequence, the critical limit, I'm sorry, may help to understand the values obtained by other authors. And this is also true because we know that many B stars are B stars and do not rotate at the critical limit or slightly below, maybe 0.7, 0.6, or less in some cases, perhaps, in particular for early B stars. So this is basically the point where we are now, almost there, with the people in Geneva. And in parallel, Maziar and Carol Jones in Canada were working on the contrary approach. And it was very nice, like they contacted me. But at some point, these two projects meet in this point. They were trying to understand whether or under which circumstances the viscous decretion disk models can approach the angular momentum loss rates from singular stellar evolution group, and of course many more things. But this is one of the things that we were trying to consider at the moment, and Maziar is working on this. So if we put extreme conditions for the models in the viscous decretion disk model frame where they're working, similar to Rimolo, but considering instead extreme values, alpha is equal to 1, a large duty cycle, omega is close to critical, and setting a broad range of stellar parameters for each mass, considering they can be in different moments of the main sequence. We can change the radius, the temperature, different parameters for them, for each mass, whether it's in different moment in the main sequence. I'm sure I'm forgetting about some more parameters considered by him. But what he obtains is that this distribution of points there, and the red point is like an average curve representing all these points. And he did this considering the galactic, the parameters for galactic B stars. And he obtains that, in fact, the average of all this distribution falls very close to our Geneva curve, which was the green one of 2013. So I think that this shows that, in fact, the Geneva angular momentum loss rates, as we already knew, were in extreme conditions, very steady disk, everlasting, they're rotating, critically rotating stars. So this at some point shows that those values were not that bad for the assumptions that we have made. Or these are representing the same thing, I would say, which is nice, I should say. And of course, real B stars may or may not resemble some of these models. So I think I spoke very fast. My English is rusty these days, and I think I missed half of the things that I wanted to say, but I can say them when we talk about this in a minute. But basically, what we have is that single stellar evolution models allowing for a progressive mechanical mass loss before the star reaches the critical limit lead to angular momentum loss rates that agree with values derived from observations, in particular with those with Rimulo 2018 and Vieira 2017. And this kind of mechanical mass loss is in agreement with, or agrees with the fact that many B stars may be rotating below critical, in particular among early spectral types. And also, as we showed in the last picture, I didn't want to show more things. I don't want to spoil Mazier's results. But in extreme cases of the viscous decretion disk models, we see that they are quite consistent with the genic single star evolution models, in particular with those 2013 or our models without the new prescription. Okay, I think this is more or less the last things I wanted to say. Of course, we have completely overlooked the binarity or other things that could help the star lose mass, or the way these rotating stars formed. I haven't said anything about this. Maybe we can talk about this now, but no, yeah, I haven't said anything about this. And just thank you very much for being there. And I think I spoke really fast today. Thank you very much. I will stop sharing. Okay.
Thanks very much, Anahí. So we have lots of time for questions if somebody wants to either raise their hand, or Mark, I'll let you facilitate the questions, or provide a question in the chat if you wish.
Thank you, G.
Okay, well, if no one else has a question, oh, Yuri's got his hand up. Go ahead, Yuri.
Hi, Anahí. Nice talk and nice work.
Thank you.
And a question. The point is that if you have a star which is mechanically losing mass, then the amount of angular momentum lost is just given by the evolution. So you need to lose such angular momentum to avoid the critical limit, or somehow stay close to the critical limit. So my question is, how have you managed to decrease this angular momentum loss? Is it by assuming that the angular momentum loss phase loss its duration is longer, or why physically is it different?
I don't think, can you repeat the question? Because how, you mean in this, in the code for our last prescription that we mentioned?
Yeah, I am just interested in, because in the fact how you managed to decrease, what is the physical reason why you decrease this angular momentum loss? Because to me, this is given by the parameters of the star, by the star evolution. So yes, how this was decreased? And
well, yes, basically in many of the models, in particular, what I consider is that the flow, or the flow of angular momentum towards the surface of the star is the same whether you put the limit strictly at 0.99 or if you put it at 0.7. But of course, when the duration of the time of the critical phase, before it was just when it was rotating critically. So it was a smaller period. Now you have a large period where basically you will removing, of course, more because you start before, but in the end, the global budget is more or less the same. You have a range, you have a broader range. You have like a, if you go to the, well, can I show it? Let's see that if we go to, can I go to the, presentation again. I don't know if you, yes, I'm sharing screen.
Yes, we
so
can see.
Now, if we go here, you see that this new, we marked here different, like these rectangles. We have a range for the same model of 3 different slots of angular momentum lost. They last differently. So that we have a small value and a larger value because you have the same amount of angular momentum, if you want, in a different period of time. That's the reason why we have different values. Yes, it's because they last differently.
Yeah, thanks. This makes sense. Then maybe you can try to calculate the number of predicted BE stars and compare this with observation, and it should be higher.
Yes,
it's another observation of signature.
Yes, and the thing is that one of the consequences of this is that we expect stars that rotate closer to the critical limit to have a larger angular momentum loss rate. That is one prediction of this prescription so far. Arbitrary.
Thank you.
Thank you.
Oh, there's another, Mark, I'll let you, I see another hand.
I don't see.
Yeah. Am I audible? Yeah.
Hello?
Hello. Yeah. Am I audible? Hi, Anahí.
Hi.
Yeah, it's a wonderful talk. So this is Gaurav from India. So actually, I might have missed, but it's a general query. So have you considered any effect, suppose metallicity, by which can actually affect, or whether it can affect the angular momentum loss rates? Because if you go to SMC, LMC, then fields and clusters, you will see the metallicity is changing. So any consideration might be that whether metallicity can affect, or any other factor which can affect, as you have already pointed out some other factors, but I might have missed, maybe.
No, in fact, yes. So far, we made these computations. We fixed the metallicity, the metallicity, but we haven't explored in fact, this prescription may be different for different metallicities, and this is what you are saying, or do you mean the general, the prescription when it reaches the critical limit? The one we use assumes the star rotates critically. But of course, the things that for the moment we have this, this prescription, the simple prescription, we explored it for SMC metallicities. So not for the whole range, but it may be interesting for the same, assuming the same prescription, see if there is an effect in the metallicity. Yes,
that can be a future prospect. Yeah.
Yes, I don't. Yes. I will check, or I will think about this. I think I did different things, but the effect is the same in the sense that we can achieve smaller angular momentum loss rates if we have such a prescription. If we allow the star to lose to start losing mass before reaching the critical limit. But yes, maybe quantifying the effect with metallicity is a good idea. Yes, you're right. Thank you.
Yeah, that's wonderful. Yeah, nice. Thanks for the talk.
Thank you.
So Anahí, there's a question in the chat from Jonathan Lebede Bartz, and I'll just read it.
Okay.
It says, thanks, Anahí. The R modes you mentioned seem very common in hot rapid rotators, but these R mode positions always retrograde in the co-rotating frame of the star, then they might instead act to decrease the angular momentum loss instead of actually helping the star to eject mass. That's what he's suggesting.
Yes. I cannot comment on this deeply because I need to sit seriously. I need to enhance my formation in pulsation and the effects of pulsation. But we talked to Sayo in relation to this because we wanted to know, as he proposed such a thing of this, the possibility of having these modes helping putting material outside the star. And he said, I cannot repeat his explanation, but he said that the process may help not to reduce the angular momentum of rate, but increase them at least in the rapidly rotating star. But I cannot myself explain this because I'm not absolutely in the field. But of course, I don't think this is the mechanism. I just put this star, perhaps some mechanism, but of course there are others. I see different names around, and I can see Luis Balona is there, and I've read his articles recently, and I'm sorry, these past years I missed the literature. Lack of internet, babies and things of my life. I'm just running behind the papers that are available, trying to catch up. But yes, I know that there are different visions on what can be causing this. But the thing is that so far, what we are proposing, or the mechanisms that we are proposing in the code, are mechanisms that are not changing the evolution of the star. And this is very important in our frame of work. Either this tiny angular momentum prescription we propose, or the ones that we had before when the star loses mass critically, whether we change that a little bit, this does not change the evolution of the star significantly. So what underlies below, I don't know how to say this, but behind that is that the star, there's something perhaps in the outer parts of the star, which is not affecting what is occurring in the core of the star. I don't know if I'm clear with this, but what we are proposing here is things that do not significantly affect the evolution of the star. And I already forgot about the question on the air modes. Yes, I cannot answer about that. I'm sorry.
Thanks, Anahí. Dietrich's got his hand up. Go ahead, Dietrich.
Yeah, thank you. First of all, Anahí, thank you for a very nice talk on a very exciting piece of work that really resonates with what I believe I'm seeing in BE stars. You mentioned binarity and offered that you would tell us a little bit more what you think about this. Perhaps I can provoke such a statement by telling you what I think, and then you correct it, please. Namely, I believe that it doesn't really matter how a B star has acquired very high angular momentum. Once the angular momentum is high, then your mechanism will work anyway, irrespective of how it acquired the angular momentum. And probably binarity enters in the transfer of angular momentum from a companion star in an earlier phase. But would a companion star still play a big role in the phases of the star that you are studying? Because the evidence that we have is that all these companion stars seem to have very low mass, much lower than the mass of a B star.
Yes, I should say that I absolutely agree with your first statement in the sense that if, of course, I cannot imagine the moment where two stars come together. I can only imagine that we have an outcome at some point. We have two stars, we can imagine in a cluster or in some dense region of stars forming. And once we have these stars formed, I can imagine that mass loss can occur. We have I don't know how this core, this new core forms, whether this sets pulsations within the star, or whether it leaves the core doing funny things. I don't know. But what I imagine is that if the physics that is governing the models that we have represents somehow reality, as you mentioned, we have something rotating rapidly. We will have strong meridional circulation. We will have all the mechanisms acting there, redistributing the angular momentum and settling a new profile within the star, which will resemble a star that has been single since it acquired since it accredited its mass. And I have this in mind maybe because in 2014 with Lionel Hamerlet in Geneva, he was computing pre-main sequence models for B stars, and we were trying to compute stars that reached the main sequence with a higher angular momentum content than we had in our previous models. What happened in the models of 2013 and many of the Geneva models is that to start the evolution, we have a star that is solidly rotating. And when we switch on rotation, differential in radius, not in the surface, but radial differential rotation, we have a readjustment of the star. So we have a decrease in the angular momentum growth rate, and may even for the moments that were rotating the fastest, we fall back to 0.9 of the critical rotation. So when Lionel he was finishing his thesis in Geneva, and he was computing pre-main sequence models, and he said, okay, let's compute a pre-main sequence structure with a very large angular momentum content, and he did that. And what we found is that no matter what, he had his computations, and I had my, or I always work with arbitrary things. It's the things that I can handle at some point. I had maybe not a solid rotation profile, but a very simple other structure. Whether I had this, whether I had mine, if the same angular, if the content of angular momentum was the same, if the star has the physical processes that we have, it will readjust to the same structure and then evolve the same way. Nothing matters because it restructures and it goes to a star as we know it, and then it evolves. Of course, you can have differences in the composition if the stars were evolved or things like that. But regarding the structure, if it goes to a stable, quasi-stable situation, then it will evolve like a single star, as I see it. But maybe funny things happen and we have like a wobbling core. I don't know, I cannot imagine this. And then what you asked, the effects of a binary companion outside the existing binary. I don't know. Of course, we have B X-ray binaries. But in affecting the outer disk, but not. I don't know to what extent this would trigger the B phenomenon as a whole, or I don't know the effect this will have. I think these are things that affect the disk, or the companion affects the disk. But I don't know. Maybe if it's close enough, it can lead to some activity or something happening outside the star, which can help matter to be released. But I don't know. I don't have an idea on the companion or the direct effect on the companion gravitationally when it needs to be very close in order to trigger mass loss, I think. It will affect the disk, but it may affect the disk, but I don't know whether it will affect the angular momentum loss rate of the star. Angular momentum loss of the star.
Yeah, I would agree. Thank you very much.
Thank you.
Anahí, Jerry Peters has got her hand up, so go ahead,
Okay.
Jerry.
Hi, can you hear me?
Yes, I can.
Okay. When you mentioned binary mass transfer, it brought me to life here. The situation is quite complicated, but briefly, here is the overall scenario. Mass probably 50 on up. Early B stars are formed as binaries, close binaries. And as binary mass transfer commences, the initial situation is that the stars get closer and closer together. Then when the mass ratio is equal, then they start pulling apart. Well, there's a certain interval there in which, you know, on the way in and on the way out, in which the gas stream strikes the gainer tangentially. And in that case, most of the mass that's and angular momentum associated with it that comes in also goes out. But the most, you know, there's a great systemic mass loss. But in the, you know, before and after that, okay, let's say before, when they're very, very close, the situation is that the mass, that the gas stream strikes the gainer at a steep angle. And there we have a substantial mass gain and substantial angular momentum gain. So I suspect it's in that stage that you have most of the spin up of the mass gaining B star. So yeah, then, you know, as it pulls apart, what happens is the residual mass transfer feeds the disk. So it's a very complicated evolutionary scenario, but one that hopefully one day we'll be able to study in more detail if certain spacecraft get approved. So anyway, I was wondering if you played with evolutionary models involving mass transfer.
I did play. It was very fun, but it's very tricky. I wouldn't say I handle completely the angular momentum transfer process. I could play with a very preliminary version of the binary code in Geneva, which I haven't asked if it's done, it's finished or advanced yet, but it was considering the rotating star, the rotating gaining mass star, both stars, and that was very tricky, handling rotation in both stars and how this rotation of the star itself interacts with orbital angular momentum. Yes, it's very tricky. And then if you start to have common envelope and you start to have losses, you need to parameterize things into the mass that is lost and the angular momentum that is lost. And basically you can do many things or whatever you want to say it in other ways. Anything can happen at that point. But as you said, yes, we can have a star acquiring angular momentum and reaching the critical velocity at that same time. But then you also have a strong, when you have a steep angular momentum gradient, I don't know how to say this anymore, but you have a rotation, a rotation profile, it needs to readjust within the star. The star will detect that you have something happening in the outer part and will try to send this towards the inner part of the star. So, of course, if you are in the outer part, you may have this angular momentum not knowing that it had to go inside yet, and it depends on whether it is that it can form something there. But I think, as Dietrich said before, that the star gains angular momentum. Some things funny happen there. It loses mass either by winds, either by common envelope, either by a BE process when this is happening. But I think that this will be relatively short in relation to the posterior phase when it has acquired angular momentum, has restructured itself, and is again putting angular momentum outwards. But then, of course, I don't know how all these things interact with the orbital parameters and orbital rotation.
That would be a very exciting project to do. And indeed, I agree that it's going to depend upon the parameters, initially. What happens as a star gets spun up by mass transfer. And, the time scales, as you point out, are very important too. In some cases, you can lose a lot of mass from the system in a short period of time, evolution, in a evolution sense. And in other times, it's kind of slow and steady and deliberate. And it will depend upon the original mass ratios, the original separation. And in some cases, I don't think there is a common envelope. I think that the stars just, based upon meager observations, consider things like, I don't know if you know about SB-SEN, but, in that case, pre-mass reversal, and the system is losing a lot of mass right now. And it's probably just very, very short, because we don't, we're hard pressed to find these systems in that state. I know of one, SB-SEN, that's losing a lot of mass in the pre-mass reversal. And there's another one, SX Origi, that's, probably, it could be pre-SB-SEN or it could be post-SB-SEN, but it's not losing much mass at all. And that it should be. But that implies to me that a lot happens in a very short period of time. So in a model, you're going to have a situation where you have a certain mass ratio and certain stars, and angular momentum in the orbit and in the rotation. And then in the next model, since you can't follow it probably can't follow it in steps of 100 years or something like that, then the next model, things are going to change really rapidly or dramatically. Better, and you're going to have a different scenario. And how long does it take the angular momentum that exists beforehand to work its way down to the interior and make a difference? So it's a very exciting, it's a very exciting time in the evolution of close binaries, and it may be more commonplace than not. So,
Yes, it's very interesting.
I can't remember. Oh, by the way, it's wonderful to see the names of longtime colleagues on the participant list, but it's it's something that I really encourage you to pursue in the future, because you can have a situation where where things dramatically change very quickly. There was somebody, I don't think it's in any name on the distribution list, but I remember a discussion at one conference, and somebody mentioned to me that they thought that single star evolution was a myth. So, that's a very dramatic statement, and I can't remember who that person was. It was somebody that used to go to BE conferences like around 1990 or so. So anyway, thank you very much for a very, very inspirational talk.
Thank you, Jerry.
Thanks, Jerry. I am cognizant of the time. Our time is getting short, and there are a few hands still up. And I don't know, Dietrich's hand is up, and so is Ken Gailey's. I don't know, Dietrich, if yours was from before, but let's let Ken.
It would be a second question if you agree.
Okay, well, let's let Ken ask his question, and then we'll scoot back to you as long as you guys can be concise. And if Anahí has time at the moment, then we'll
No problem.
get the last few questions asked. I don't want to hold people up too much longer than their
And
time.
mine's going to be real quick. I'm just wondering if you had access to any observational technology that you don't currently have access to, what would it be that you would want to know the most about these systems?
You mean me?
Yeah.
For B stars? I would like to know what is happening in that very tiny region between what we know the innermost part of the disk and the star. The disks seem to be pretty well observed, and also we go to the other extreme, the outer part of the disk, what's happening out there. But then if we go if I had one choice in my life to say what I would like to see is this part. If this is the only thing I can see in my life, is this innermost part, and see what's going on there. But of course, for many different stars, for many different stars.
And given that you can't fly there, what do you think would be the best observational attempt to do that?
Observational attempt to see this.
Like what kind of
well, there are many available observations that can give us different things, like observe the photometric variability is very interesting, which gives us an idea of different parts of the disk. Together of spectroscopic, I really don't know the details of the lines that should be observed in this particular region. If I think of what in my mind is related to the innermost part of the disk, which is maybe, I don't know, perhaps iron two lines, or this kind of lines that form in this very dense and innermost part of BE disks. Of course, there are many of these observations, but there are many of observations of these lines. They're different photometric observations. Perhaps it's me that I don't have the answer because I haven't studied enough. I know that many people may have this their own understanding already of all what's happening there. I need to study more perhaps, and to see what the data gives and to see what other models give. But I think that having all these kind of observations for different stars seen from different inclination angles would give us a better understanding. And also, what I think is very important is to study, to try to understand the BE phenomenon in relation to the ambient where these stars appear. Why do we have these clusters like NGC 663 with all the B stars being BE stars, and why do we have other clusters of the same age, same chemical composition that do not have the same fraction of BE stars? What is there? Why? Is it that they were all binaries that suffered mass transfer? No, I don't think that's the case. Is it? I think it's more related to the conditions of the clouds that form the systems, or where the systems are in the galaxy. I think that more needs to be studied in the ambience where B stars live. Maybe some people have done this. I'm trying to go also in this direction with some people working in galactic dynamics. And I don't know, these are different paths, but I think that trying to understand the origin of rapid rotation exceeds a star itself or a binary. It has to do where the ambient where the stars formed. So I think I didn't answer your question, but it was a very nice
no, that's a great answer. You want to know, you want to observe the larger context of the system. Okay.
Yes.
And the innermost region where you'll see it in the polarization and in the UV, Ken.
Of course.
Right.
Of course.
Gotcha.
Okay, I guess we'll let Dietrich have the final word. We're really pressing out. I realize some people have had to run off. That's fine, but go ahead, Dietrich.
Yeah, I will keep the question short. In many BE stars, we see activity cycles where they eject matter and then they're more quiet for a while and they eject matter again. And do you see in your models some such limit cycle, or can you make your models see them that the star ejects angular momentum, then relaxes because there is no excess angular momentum at the surface because it has been ejected, until the angular momentum reaches the surface again, and then a new outburst occurs?
The thing is that we have, if we want to see the whole evolution of the star, we have time scale, which is the smallest time scale is much larger than the typical outburst time scale of a B star. But yes, at some point, I think it was, we tried to reduce the time scale, the time step of this. And at some point, I think we did, but the thing is that we can see the picture in the, I don't think that the evolutionary code has the ingredients or the physical mechanisms that act in this like a tiny pushing to the material side. It helps with you have the shears, which is the main perhaps effect affecting this transfer at this mechanical mass loss rate, mechanical mass loss period. We have the shear that is the most important effect acting there. But I don't think, and it has, of course, it has some, of course, when we lose an angular momentum loss rate and we go below critical at some point, perhaps in the next time step, we will not lose mass. But in the end, we'll have this average thing. And I don't know how this relates. I don't know if this particular thing we can know currently in the current version of the stellar evolution code. I don't know. I think they are missing pieces. I
appreciate the difficulty, and I probably don't even understand it fully. But this would be very exciting to do, because that might be the first time ever that one could see in a main sequence star stellar evolution at work in real time.
Yes, you're right. And we had some numbers of these in our 2013. We did so many things in that paper, but some of them were like not. But I think that we quantified that at some point. We reduced the time step, and what we did was we put the fraction of time that the star was not losing mass, and the fraction, some kind of duty cycle, if you want. And the fraction of time that the star was losing mass. And we could see a trend with the time step. But yes, I don't know to what extent we can link that to the real outbursting nature of these stars. I think it's if we could observe B stars for 1,000 years, if we live that long, maybe we can have a better idea and try to relate these two things in the earliest, because they have they live faster, and so for very early B stars, we may be in that regime where we can see the mass being put outside. But now that you say it, and I haven't thought of this before ever, so maybe what I'm saying is completely nonsense, but I can imagine that if you cannot see one star in one moment, in a whole moment, maybe you can see many resembling stars in different stages, and I don't know, but you need stars of the same age, of the same everything, and see if something is there. I don't know. I need to think about that. But it's a very, it's nice to interact with B people again and have such interesting questions that trigger thinking. It's nice. Thank you.
I can say the same about your answers. Thank you.
Yeah, thank you very much, Anahí. You can tell by all the questions that people were very engaged and interested. I realize we've gone way over, but thank you so very much for speaking to the group. We really appreciate it.
Thank you very much.
Great talk.
Bye-bye. Thank
Take
you.
care. Bye.
Bye. Bye-bye.